Hey everyone, welcome to the video. So today I want to talk to you about this recent paper that I wrote together with Yinta Li and Xinzhi Zhang. Yinta is at Microsoft right now and Xinzhi is at the University of Washington in Seattle. So let's get started. What we're doing today is we're going to be looking at linear programming. Now, to introduce how I think about it, for me, a linear program is the task of maximizing a linear function, C transpose times x, subject to a system of linear inequalities. Ax is at most b. So here we get a, b, and c, and it is our goal to find a point x with d variables that satisfies each of the n linear inequalities. And among such feasible points, we want to find one that maximizes the linear function C transpose times x. And how we're going to do this is we are going to use this algorithm called the simplex method. How it works is that we have this polyhedron defined by the linear inequalities. And let's suppose that we get a vertex of this polyhedron from somewhere. What the simplex method will do is it will look at the edges that go out from this vertex, and it will pick one such that traveling along it makes the objective value improve. And it will keep going until it hits another vertex, and it will keep doing this repeatedly until at some point it reaches an optimal vertex. There is some computation going on here. There is linear algebra backing all this, but what we're going to be thinking about is only the geometry. If you know what it means, that means we're not going to be considering degeneracy in the linear program, just how many steps are needed along the edges of the polyhedron until reaching an optimal solution. Now, to fully specify the algorithm, I would need to also tell you where we get this initial vertex from. I'm not going to be thinking about that much today. And I would need to specify to you a pivot rule, like a rule for deciding which of the outgoing edges do I prefer to take. And there are a few different of these rules. Some of the more well-known ones in theory are the most negative reduced cost rule, the steepest edge rule. There is the greatest improvement rule. There are approximate steepest edge rules. None of these are what is implemented in like real commercial linear programming software. They have deeper secrets that we have no knowledge of. What we're going to be looking at today is a rule that is cleaner to analyze in theory. It's called the shadow vertex rule, and it's going to have some nice properties that will help us do our analysis. And so the simplex method, it was introduced in 74. The first linear program was solved in 48. And what people realized very quickly is that the simplex method is efficient. The number of vertices that is taken is roughly 2 times n plus d. This is a very solid rule of thumb, but cases where like 5 times that number are needed, there are very few documented cases of this. The question for us theoreticians is, can we prove something of this form? Can we prove that the simplex method requires only a linear number of pivot steps? These hopes, they were dashed in the 70s when Klee and Minty found this evil linear program that tricks the simplex method into visiting exponentially many vertices. And over the years, this result of Klee and Minty has been extended to almost every pivot rule that has been analyzed. This leaves us with a scientific mystery. In practice, the simplex method is very efficient, whereas in the theoretical worst case, it takes exponential time. The first attempts to try and remedy the situation were based on average case analysis. A whole bunch of people did tremendous work in this area. Today, I will highlight the work of Borgward. Pick a nice probability distribution over linear programs. Borgward decided to let the right-hand side be the all ones vector, and to pick the rows of the matrix A independently and identically distributed from a rotationally symmetric distribution. Borgward proved that there is a simplex method, which on linear programs drawn from this distribution visits order d squared n to the 1 over d minus 1 vertices in expectation. There is a lot of beautiful mathematics going on in here, but it might not actually explain our scientific conundrum. His order d squared n to the 1 over d minus 1 bound is not linear in n plus d like we were expecting. Moreover, there might actually be a meaningful difference between typical and random linear programs. To illustrate this concern, I've prepared two pictures. On the left, we have a typical picture, an all too typical picture that you might find in the news these days. On the right, a random picture. For every pixel, I sampled a uniformly random R, G, and B value. Mathematically speaking, this is a very nice distribution, but the result is only noise. It looks nothing like a typical picture. What we learn about random objects might not actually teach us anything about typical objects that we find in the world. What we might need is a method of analysis of algorithms that combines both the advantages of worst case and average case analysis. Something that combines both structure and randomness. This is what smooth analysis aims to be. Smooth analysis was introduced in 2004 by Spielman and Zhang. For linear programming, the definition of smooth complexity is as follows. Suppose that there is some LP data out there in the Platonic realm, consisting of a matrix A bar, a vector B bar, and C. Without loss of generality, assume that this data is normalized such that the rows of A each have norm at most 1, and that B has entries between -1 and 1. Now we wish to measure this data. While doing that, some measurement error occurs. We model this by adding a matrix A hat and a vector B hat to our original data. Their entries we assume to be independently distributed, and are each Gaussian with mean 0 and standard deviation sigma. Now, the smooth complexity of an algorithm is defined as the time it takes to solve the perturbed linear program. We will take the maximum over all A bar, B bar, and C, and the expectation over the noise A hat and B hat. The smooth complexity is parameterized by three quantities: the number of variables, the number of constraints, and sigma, the standard deviation of the noise. When sigma would go to 0, data is not at all perturbed, and the smooth complexity basically reduces to the worst case complexity. When sigma goes to infinity, noise will drown out any of the original structure, and we will end up with a kind of average case analysis. In the intermediate regime, we might learn how sensitive the worst case behavior is. A small dependence on 1 over sigma in the running time bound would imply that the worst case behavior is very fragile. We are going to be able to analyze this smooth complexity of an algorithm based on the shadow vertex rule. So let's illustrate the shadow vertex method on an example to see what kind of pivot rule it is. So we start out with a polyhedron, of which we have a vertex that we know, and we have an objective vector. Now we're going to find an objective, an auxiliary objective, that is maximized by our current vertex. We can obtain this by taking any positive linear combination of our active constraints. Now we're going to rotate our one objective towards the other objective, and the algorithm is going to pivot in such a way that it will always stay optimal for the current interpolated objective. So we will interpolate our objective some distance until our vertex is no longer optimal, and then we pivot. And then we keep doing this until at some point interpolated objective will hit our desired objective. At that point we will have our solution. Now, why is it called the shadow vertex method? For this, let's project our polyhedron onto the subspace spanned by our two objective vectors. So this is what we can see here, the projection. And now if we run our algorithm, all the vertices visited by the pivot rule, they exactly land onto the boundary of the projection. This means that instead of analyzing some difficult to reason about algorithm, it will instead suffice to upper bound the number of vertices that this projection has. The Simplex method with the shadow vertex pivot rule has been the subject of a lot of analyses. Already Borgward studied the shadow vertex rule. The analyses of Spielman and Zhang and Verschinnen, Dadouche and myself have all focused on this rule and analyzing it in different ways. These earlier papers, they have done a lot of work to make this reduction from analyzing an algorithm to analyzing a nice geometric quantity. They've done a lot of work to make this as concise and as clean as possible. If I were to summarize these results from the literature, it would be a theorem like this. If you use the right auxiliary LPs, then the shadow vertex simplex method has a smooth complexity given by this quantity right here. We have a number of vectors, a1 bar up to an bar, d dimensions. They each have norm at most 1. And we have a 2-dimensional linear space W. Now we are going to perturb our vectors, a1 bar up to an bar, by some noise. So for this, we're going to draw perturbations, a1 hat up to an hat. They're going to be independent and standard normally distributed in RD with standard deviation sigma. Now we have these n perturbed vectors. We take their convex hull and we intersect it with a 2-dimensional plane. How we went from projections to intersections, this is a phenomenon known as polar duality. I'm not going to get into this. But so now we have a 2-dimensional polygon. We can count how many vertices does it have. And the smooth complexity of this slice, smooth number of vertices of this polygon is exactly equal to the shadow vertex simplex method's smooth complexity. All previous people have analyzed this number of vertices, starting with Spielman and Zhang, who proved a bound of the order d cubed times n times sigma to the -6, assuming that sigma is not too large. And then people have successively tried to further improve these bounds, with most attention, I think, being paid to reducing the dependence on sigma. So you can see here that myself, Yintat, and Xinzhi, we have the new best bound so far. Another thing that we managed to do is we found the first lower bound on the smooth complexity. What we knew before in terms of lower bounds is a result from Borgward, an average case result that fits into the smooth analysis framework well enough to give a lower bound of order d to the 3/2 times square root log n. And now what we found is a lower bound construction. It works for smooth analysis. The lower bound that we can prove, it gets stronger if sigma gets smaller. And the dependence that we kind of get is 1 over square root of sigma, at least until you hit the worst case complexity. One thing that is actually kind of nice is that most of these smooth complexity results, they have an easier to understand 2-dimensional analog. So we can look at this for a second. Let's look at this question at a 2-dimensional question. Suppose I have n vectors, a1 bar up to an bar, 2-dimensional, each of norm at most 1. And we perturb them again with independent Gaussian distributions. Now we take the convex hull of these 2-dimensional points and we end up with a polygon. We can study what is the smooth complexity of this polygon, what is the maximum over the bars, the expectation of the hats of how many vertices this polygon has. As you can see, a bunch of people have worked on this, and there's a close connection between proofs here and proofs from literature that I mentioned on the previous slide. Almost exactly match up. And here you can also see that the bounds are improving, but here there was already a smooth complexity lower bound. What we prove in our paper is almost matching upper bound. The smooth complexity of polygons we now know almost exactly. So yes, our paper, we basically have 3 contributions. We have an improved upper bound on the smooth complexity of the simplex method. We have the first lower bound on the smooth complexity and a tight bound on the simpler 2D case. In the rest of the talk, I will go into a bit more detail on the lower bound. We make some new connections that I think you will enjoy. Let's start with a staple of theoretical computer science, an extended formulation. And this is actually the same polyhedron that I showed you before in the demonstration of the shadow vertex method. Upstairs, we have a polyhedron with 6 facets. If we project it onto a certain 2-dimensional space, it has 8 edges. We got some edges for free. And there is a stronger result that we can prove of this form, which is the central part of the construction of our result. What we prove is that for every k, for every natural number k, there exists a polyhedron in k plus 4 dimensions that has 4k plus 1 facets, such that if I project it onto a carefully chosen 2D subspace, then this results in a 2 to the k gon, a regular 2 to the k gon. So this is an exponential blowup. Upstairs we have order k objects, facets, and downstairs we have 2 to the k edges. As a further technical consideration, what we get is that this polyhedron P, it is like a cube. it is contained inside of the infinity ball of radius 1, and it contains the infinity ball of radius 1 over 30. If you look at just the upper part, this is a lot like a classic result from Bental and Namirovsky, and we extend it to fit our purposes better. Using a classical technique of polyhedral duality, we can turn this object into the kind that we need to fit the summary theorem from the literature. In this perspective, what we prove is the following. For every k, there exists a k plus 4 dimensional polyhedron dipolar that has 4k plus 1 vertices, and if I intersect it with a carefully chosen 2D subspace, then I will get a regular 2 to the k gon. And moreover, what we know is that this object contains the one ball of radius 1, and it is contained inside of the one ball of radius 30. Up to like scaling by a factor of 30, the vertices of this polyhedron satisfy the smooth analysis concept that we needed, where we needed these a1 bar up to an bar of norm at most 1. Here, for simplicity reasons, they are of norm at most 30, equivalent up to a constant factor. And so this is our construction, and now we need to find a way to analyze it. We need to show that if we perturb these vertices by some Gaussian error, then the resulting intersection with W will still have many vertices, or because it's a polygon, number of vertices is number of edges. So let's find a way to lower bound the number of edges of a polygon. Here is the lemma that we're going to use for this. If I have a polygon, and if it contains the round disk of radius alpha, and is contained inside of the round disk of radius beta, then T must have some lower bounded number of edges. For the proof, let's consider this picture right here. We have our polygon, we have an inner disk, we have an outer disk, and now if we consider any edge of this, such as the red one, then we can prove that there is an upper bound on the length it can have. Because if this red edge were any longer, either it would have to stick outside of the outer ball, or it would have to pierce the inner disk. You can calculate this maximum length by way of the Pythagorean theorem. Now, how do we lower bound the number of edges? Well, the number of edges of a polyhedron, it is at least the perimeter divided by the longest edge length. Think of it this way. If I want to walk a kilometer, but every step that I take is at most 1 meter long, then naturally I need to take at least 1,000 steps. So without going into the formulas, we can see that a polygon that is close to a disk must have many edges. And so we have our construction from 2 slides ago, and we know that it has this intersection that is a regular 2 to the k gon. It is very close to a circular disk. The remainder of the analysis is we need to prove that even if we perturb the vertices of this object by a tiny bit, the end result, the same slice of the end result, will still be very round. After perturbing, every slice is going to be the same, roughly the same shape as it was before. So here is the dilemma that we can prove. It's a bit more technical than the previous one. Let's go through it. So suppose there are 2 numbers, little r and little epsilon is positive, and we know that r is at least twice epsilon. Now we have a set of points, a1 bar up to an bar. These are our original points. And a1 wiggle up to an wiggle. These are the perturbed points. And we assume that we have 2 properties. One is that the convex hull of the a bars will contain a large scaling of the 1 ball. This is exactly what our construction provides. And second, we will assume that each of our perturbations has 1 norm of size at most epsilon. Then what you can prove is that the convex hull of the bars and the convex hull of the wiggles, they are close in a certain kind of distance. Specifically, if I take one and I scale it down a bit, it is contained in the other. If I scale it up a bit, it contains the other. In words, if I have an object that satisfies our technical condition, then perturbing it will not affect the roundness too much. To finish up the theorem, you take the constraint vectors from the construction, and they satisfy the conditions of the smooth analysis. The original intersection with W is very, very round, and we know from the second lemma that adding small perturbations doesn't hurt the roundness too much. And we can quantify how much exactly. And then our edge counting strategy will prove us a lower bound on the smooth complexity. And we got kind of curious. So we know that our 2D analysis is actually tight. We know that the the two-dimensional smooth complexity of a polygon scales almost exactly as 1 over square root of sigma. And we wondered, well, will this also be true for the simplex method, smooth analysis? So we did a little experiment. We took the construction that I talked about, we put it into the computer, we added the perturbations of different sizes, we did a bunch of trials, and we used Gurobi to compute how many vertices we actually get in this two-dimensional polygon that is the intersection. On this plot, you can see the results. This is a log-log plot. On the horizontal axis, you can see the size of sigma. On the vertical axis, we have the number of vertices that we measured. We did trials for both for k equal to 10, k equal to 15, and k equal to 20, and for a range of various sizes of sigma. And if we eyeball the numbers, then we will find that roughly the number of vertices of the intersection scales about as sigma to the minus 3 over 4. So that is higher than the lower bound, but lower than the upper bound. What else you can see is that if sigma gets too small, then each of the three series will plateau at some level. It plateaus around 2 to the k, exactly where you would expect it to. So I've talked about proving a lower bound on this smooth complexity. We did this by looking at the lengths of the edges of the intersection. All the previous upper bounds on the smooth complexity also looked at the lengths of the edges. For our own result, we needed to consider both the length of the edges and the angles at the vertices, and these two considerations together were enough to prove an almost tight upper bound in a two-dimensional case. In the case for general dimensions, when analyzing the simplex method, this might not be tight, as we saw from the experiments. Let me end on a few open problems. For one, we know that there is a gap between the lower bound and the experimental result, perhaps also between the experimental result and the upper bound. So, and tighter bounds would of course be better. From a scientific point of view, I think the big open problem in this space would be to see, can we prove smooth analysis kind of bounds with sparse noise? The reason for this is that real linear programs are sparse. Their constraint matrix A, it consists of mostly zeros and maybe less than 1% of non-zero entries. Whereas the matrices that we're analyzing in smooth analysis, they are dense. They are, with probability 1, there is not a single zero in there. It would be really interesting to see if the conclusions of smooth analysis could be extended to some model of sparse matrices. I must say that even asking the right question is not exactly easy here. One step beyond that would be to look at real software. Actual implementations of the simplex method, they will actually perturb the data in some cases. They do this by perturbing the right-hand side vector, and this helps to speed up the simplex method. And we might wonder, can we prove anything about this? Can we prove that with some small perturbations over there, the simplex method will speed up? That's it. Thanks for watching.